So let's start today's seminar. Today's seminar speaker is Professor Silvia Pascoli. So thank you very much for giving us a talk. And the title is Sterile Neutrinos, Indication and Tests.
Okay, thank you very much for, should I start?
Yeah.
Yes. Thank you very much for this invitation to talk about this recent paper that I wrote with my student and former postdoc. So what I'm going to focus is on sterile neutrinos, so minimal extensions of the standard model. And I'm going to discuss what sterile neutrinos are. Oh, now it's not working. Yes. What sterile neutrinos are, to set the formalism and to look at their consequences in terms of neutrino masses and in terms of the phenomenology. I want to do that first because then I'm going to go to the core part of the talk, where I will argue that these extensions of the standard model, which have multiple portals, are a very natural way of explaining a variety of experimental issues. First and foremost, neutrino masses, and in case also dark matter. But they also can explain a variety of anomalies that have emerged in recent years, and they do that in a coherent framework. So the basic idea at the core of this talk is that there is a hidden sector, and this idea has emerged and gained a lot of attention in recent years. So with the intensity frontier and the basic principle that there are new particles, new sector, which is very weakly coupled to the standard model and therefore has not been yet discovered. And in order to test it, one has to go and look for more precision and higher intensity beams, in colliders, beam damped experiments, neutrino experiments, and so forth. But I want to put a twist to this idea because what has been considered so far has led to the basic picture of FIPS, the feebly interacting particles, in which there are several portals. There's the neutrino portal, the vector portal, scalar portal, axion, mainly charged particles, dark matter. And the one looks is at each individual portal and assumes that the interaction of this portal is very weak, allowing for very weak interactions between the hidden sector and the standard model. But this, in my opinion, this is a minimal picture, but not necessarily the only way in which we can look at a hidden sector. Indeed, there could be very strong interactions in this hidden sector. After all, the standard model is a very complex structure. It has multiple fermions, there's a complex gauge group, there's one scalar. The hidden sector could have also a rather complex picture with multiple particles, multiple interactions, etc. In particular, in my opinion, a three-portal scenario is, in a sense, the most natural one. And it centers around the extension of the gauge group through new gauge interactions. But the moment we do that, we need to extend it by a scalar sector, which needs to break the symmetry. So already we have two portals, the vector portal and the scalar portal. And for really, in order to exploit the dynamic nature of the gauge symmetry, then you need new fermions which are charged under this symmetry. So we have then a dark fermions, which allows for the neutrino portal as well. So, and when, as I will show you later, when you have the three portals together, the theoretical consequences, for instance, neutrino masses, and the phenomenology can be drastically different. And indeed, we exploit this synergy between the three portals to explain various anomalies, as I will discuss later. G-2, MiniBooNE, and a variety of other less significant hints of new physics that there are. So let me first start, however, with the standard picture of heavy neutral fermions to introduce the formalism and what are the basic characteristics, so that then I can confront these with the richer phenomenology that I will discuss in the case of a three-portal extension of the standard model. So what I mean with sterile neutrinos are neutral fermionic singlets of the standard model, and I will call the flavor states sterile neutrinos. So I extend the 3 active generations with a sterile and possibly more than one sterile state. And I will call heavy neutral leptons the corresponding mass states, and the two are related by mixing, as in the case of standard neutrinos. The heavy neutral leptons entered in the charge current Lagrangian via the mixing between the massive state and the active neutrinos. And therefore, via this, they feel weak interactions, although suppressed by the small mixing angle, both in the charge current and neutral current components. And through that, then we have all the relevant phenomenology in terms of detection, signatures in experiments, and etc. Okay. So adding sterile neutrinos to the standard model is a very simple and minimal extension to it. The theory remains anomaly-free, and moreover, it can explain the origin of neutrino masses through a seesaw. And I should mention here that the seesaw picture can advocate new energy scales from the GATT theory down to the EV scale. And in recent years, a lot of attention has been put in the TeV to KV region, as this has a lot of phenomenological consequences. If one prefers a very high energy scale, then these sterile neutrinos can be embedded in GATT theories. For instance, they are predicted in SO10. Now, there is no strong theoretical or experimental indications for choosing one scale against another. It is a more theoretical preference and the type of consequences when one can get. For instance, at very high scales, 10 to the 10 GeV or so, then these sterile neutrinos can be responsible for the baryon asymmetry through a standard leptogenesis mechanism. But at the GeV scale, this is also possible now through leptogenesis via oscillations. I should mention that by naturalness, as the masses of these sterile neutrinos break lepton number by 2 units, by setting these masses to 0, one restores lepton number. So if some prefer the low energy scale for this reason, but as I said, it's pure theoretical personal preference. So what are these sterile neutrinos are going to do good for? Well, they can explain neutrino masses, and I will spend a few minutes on this to show then how one can generate the right mass scale and the right mixins, as I will use this later on in the three-portal model. As I already mentioned, they can explain the baryon asymmetry. And in some cases, in particular, if one of these sterile neutrinos is at the KV scale, they can constitute a dark matter candidate, specifically a warm dark matter candidate. But this is not necessarily compatible with these other, I mean, it's compatible, but not necessarily justified in view of these two other consequences. So let me talk for a few minutes about how the introduction of sterile neutrinos in this extension of the standard model can induce neutrino masses. And this is a key problem, actually, in my opinion, is the only evidence we have of physics beyond the standard model in particle physics. Of course, we have also dark matter in astroparticles. And we have to explain these neutrino masses, advocating some extension of the standard model. The simplest way we can do that is to introduce a right-handed neutrino. Can you see my cursor?
Yes.
Yes, okay. This right-handed neutrino, this sterile neutrino, this is a singlet of the standard model, so I can write down this Dirac with this Yukawa coupling, and when the Higgs gets above, this will lead to a Dirac mass for the neutrinos. There are two issues, well, not issues, but one issue is that the coupling needs to be extremely small. And for this reason, unless there is a good explanation for the smallness of the Yukawa coupling, a lot of theories don't consider these the ultimate answer to neutrino masses. But I argue that this nevertheless is an extension of the standard model. It's not just introducing a right-handed neutrino, but is also imposing lepton number as a fundamental symmetry of the theory. which in the standard model is not. In the standard model, lepton number is an accidental symmetry. While here, to prevent a Majorana mass term for these right-handed neutrinos, there are singlets, and therefore I can naturally write down a Majorana mass term. To prevent such term, then I have to impose lepton number. So this is, for me, is a very significant departure of the standard model, because I'm modifying the symmetry structure at the core of the model. So the other possibility, as you well know, is to introduce Majorana masses, and this can be achieved introducing the only dimension 5 operator I can to the standard model, which is the Weinberg operator, which contains two leptonic doublets, and when the Higgs gets a web, this gives exactly a Majorana mass term to the light neutrinos. Of course, as this is a dimension 5 operator, it needs to come from a higher energy theory. And indeed, there are different ways in which I can open up this effective vertex here. And these are denoted CISO type 1 when the exchange is of a fermionic singlet, CISO type 2 when the exchange is of a scalar triplet, and CISO type 3 when exchange is a fermionic triplet. For the purposes of this talk, I will focus only on CISO type 1 and its extensions, because that's what I will use later on to explain neutrino masses in the three-portal scenario. And so one introduces a right-handed neutrino as before, with a Yukawa coupling, with a leptonic doublet and the Higgs, which is allowed. But if I don't impose lepton number conservation, then I can also write down a Majorana mass term for these sterile neutrinos. And then when the Higgs gets a web, this leads to this mass matrix, which needs to be diagonalized, leading to the famous CISO formula, where the masses of the neutrinos are given in terms of the Dirac mass squared and a heavy scale in the denominator. If one takes one embeds this in a typical gut theory, one will have for the Dirac masses something of the order of the other fermions, for instance, the tau, so 1 GeV, and this requiring a mass for the right-handed neutrinos around 10 to the 10 GeV, which is very nicely compatible with leptogenesis, give a mass for the neutrinos in the right ballpark. So here the smallness of neutrino masses is related to a very heavy scale without requiring any small parameters, any tuning of the couplings, for instance. And so for this has emerged the standard explanation of neutrino masses. I should mention that the coupling, the mixing between the active neutrinos and the heavy neutrinos is very small. And so prevents the testability of these type of models. If one wants more larger mixing, then one has to lower the scale here or the heavy mass. This is possible, paying the price of requiring smaller and smaller Yukawa couplings. There's another way, which is also to extend the CISO model with more than one type of sterile neutrinos. And indeed, this is what I will do in the dark in sector model I will discuss later. So if we introduce, for instance, two types of sterile neutrinos, nu1 and nu2, then one can write a generic mass matrix of this kind once the Higgs gets a web. But the beauty of this mass matrix is that, for instance, if these two parameters, with these three parameters here, are very small or set to zero, actually, the mass of the neutrino is zero. This is a cancellation of the contributions of the two sterile neutrinos to the mass matrix, to the light neutrino masses. But this cancellation is not a tuning, is actually related to the conservation of various lepton numbers depending on the charge assignment of nu1 and nu2. And in fact, the neutrino masses then here depend on these parameters mu, this y2, and at loop level on mu prime. And so these parameters are naturally small because they correspond to a small violation of lepton number. And in this way, one explains the smallness of neutrino masses in terms of a small breaking of lepton number. There are two particularly interesting limits of this picture. One is the inverse CISO, in which the two sterile neutrinos constitute a quasi-Dirac pair with large mixing between them. and the extended CISO, in which instead one has a CISO also in the dark sector. And in this case, one neutrino is going to be very heavy, and one can explain a relatively light sterile neutrino due to this CISO into the dark sector. But the mixings are much larger than in the case of a standard CISO, as they're controlled by different parameters. And this is interesting because then having larger mixing means enhance the stability of this type of models, as these particles can be produced in Z primes, in CISO type receptor. So what is the type of signatures then these sterile neutrinos have? And I'm going to discuss this in quite some detail, because then I want to confront to the phenomenology of the dark neutrino picture. And I'll show you that it's indeed quite different. So let me start with this vanilla heavy neutral lepton, so the standard picture that I discussed so far, in which I don't introduce additional interactions. And the signatures depend on the mass scale of the new particles. If we are extremely heavy scales, then here one can explain the baryon asymmetry, and there will be other indirect consequences of the model, not of the heavy neutral lepton directly, but of the overall picture. In gut theories, we will have proton decay, and in some cases, depending on the breaking of the gut theory down to the standard model, there could be gravitational waves due to cosmic strings. If we lower the scale, then at the TV scale, then this can be tested at colliders. And indeed, there are many results from ATLAS, EMS, LHCb, which look for heavy neutral leptons at LHC experiments. And lowering the scale further, when we go into the GeV to MeV range, one can look at them in decays, as I will discuss, peak searches, neutrino S double beta decay, and a variety of other consequences. And for the lowest scales, we have kinks in beta decays. For example, Catherine is going to do a search for very light heavy neutral leptons. Here is also where dark matter sits, neutrino masses, neutrino oscillations, and so a very rich picture. I will focus only on those signatures that then could appear also in the dark sector model that I will present later. And here a key bound is that of peak searches. The idea is that one looks at pion and kaon decays. For example, a pion into, well, here is E neutrino. And if this neutrino is a heavy neutral lepton, and this will happen with a fraction proportional to the mixing angle squared, then the energy of the electron will be lower, and one will have a tiny peak in the spectrum. These are nearly model independent tests. Indeed, up to a couple of years ago, I thought it was impossible to beat these bounds that were completely model independent. And then a consideration of at the time, my student Matteo Soster, actually from an experimental point of view, suggested that this is not the case. And indeed, we have done some analysis. It's possible to weaken some of this bound by a factor of at least a few, if not some factor of 10, 20. And I will use that indeed when I talk about the dark sector. But in any case, these bounds are extremely strong and come from both pion and kaon decays, as you see here. We have lepton number violating searches. We have neutrino S double beta decay, but for specific ranges of the masses, the bounds can be extremely strong because this process can go on resonance on the intermediate heavy neutral lepton. And these type of searches are done also in kaon decays, BDKs, and at colliders, looking for lepton number violating and lepton flavor violating signatures, but no excess has been found so far in any of these searches. Indeed, although I'm going to discuss it in this talk, but it's present in the paper, actually neutrino S double beta decay puts some significant constraints on the model if one switches on the mixing with neutrinos at a sizable level. The other main way to detect these or to search for these heavy neutral lepton is via decays. And the idea is that somehow these heavy neutral leptons are produced and then they will decay via their mixing with the active neutrinos. They, as I already said, discussed, these have charge current and neutral current interactions also suppressed by the mixing angle squared, but nevertheless, they can decay into visible particles, typically leptons, pions, pi plus, pi minus, pi zero, etc. And then these particles are visible in the detector and they have very specific features. As the ends are quite boosted, they will be very often very collimated. They have, and they are very visible. For example, the typical channel is pi plus muon, which are two particles which are easily detectable in an experiment. And indeed, these put very strong bounds on the models. So there are two main strategies. One is in beam dump experiments where you have a proton beam impinging on a target. This produces pions and kaons which decay into neutrinos, and with a small fraction related to the mixing, these will produce from time to time a heavy neutral lepton, and then this heavy neutral lepton interacts very weakly with the background, goes through some dirt, and then can be detected in the in a detector where it can decay. And this is the strategy which has been used mainly in the 90s, and PS191 remains the most sensitive experiment for a wide range of masses. But now there are new experiments, for instance, Na62, as well as a variety of neutrino accelerator experiments, which can be used in beam dump mode, because indeed they have a proton beam, they produce lots of pions and kaons, and then they have a near detector complex, which can act as the detector for this type of searches. For instance, in MiniBooNE. As I mentioned, this is PS191, which remains the kind of the most sensitive to date. But as you can see, the DUNE near detector and SBND at Fermilab, Na62, and of course SHIP have parameters in terms of volume of the detector, which is the parameter which matters, energy and protons of target, which are competitive with PS191. And indeed, they will be able to improve on these bounds. The other strategy is scattering. In this case, is the neutrino beam itself, which interacts in the detector, in this case, producing one of these heavy neutral leptons via neutral current interaction. And then the heavy neutral lepton, if it is decays sufficiently fast, will lead to a signature. And this is the strategy which has been adopted by CHARM2, which is this kind of light green bound in this plot that I taken from a paper of a few years ago, but the picture has not changed very significantly since, apart from some bounds from an A62. And this is a summary of the current status with the sensitivity of SBND, which is this blue line here, Na62, SHIP. As you can see, Na62 and SHIP will be able to improve on the current bounds very significantly at high masses due to the ability to produce lots of new taus. And DUNE is this line here, which will be able instead to improve on the current bounds at lower masses. So there's experimentally, we can expect significant improvement in the coming years. So now I've set the basic picture of heavy neutral leptons and what are their theoretical consequences, mainly neutrino masses, and their phenomenology. But now I want to go to the core part of the talk to discuss this idea that I already mentioned, that heavy neutral leptons could be part of a rich dark sector, which contains several new states and interactions. And for me, at the core of it, at the center of it, is a new gauge interaction, in particular, the simplest extension that I can do, which is via U prime. This necessarily, we have a gauge sector, in particular, a Z prime or dark photon. I will call it in on an equal footing throughout my talk in this way. That I have to break the symmetry, therefore I need a scalar sector, which gets a wave, giving mass to the dark photon. And as I said, once I have a new gauge symmetry, which has a dynamic nature, for me, it is natural to introduce a fermionic sector, which is charged under this, and therefore feels this new force. And I will call these dark neutrinos. These are charged under the new one, the U1 prime. And this is kind of this three portal picture in which we have three then portals to the standard model. And as I will show you in detail, the phenomenology of this kind of model can be dramatically different to the standard one that I discussed. So first of all, there is the neutrino portal. So we have these dark fermions, but then the theory does not prevent to introduce the usual sterile neutrino, which is a singlet compared to the standard model and compared to the hidden sector. So this is kind of the communication link, the bridge between the standard model and the hidden sector. Once the Higgs get a wave, there will be mixing between the standard model neutrinos, the sterile neutrinos, and the dark neutrinos, and this will induce the neutrino portal with very weak interactions due to the small mixing. As we have a new scalar, this term, phi dagger phi, h dagger h, is allowed in the theory, and therefore this will lead when the phi and the Higgs gets wave mixing between the Higgs and the new scalar, and this leads to the Higgs portal. And then we have a new gauge field, and therefore I can write down this kinetic mixing term, which will then induce a coupling of the dark photon or Z prime with the electromagnetic current. Therefore, I want to mention this because it's very relevant for what I will do later. There's no direct coupling of the Z prime to neutrinos, to the usual neutrinos, to active neutrinos, as these are not charged. The active neutrinos can couple to the Z prime, or not the active neutrinos, the light neutrinos can couple to the Z prime via mixing to the dark neutrinos. So, and this is the specific realization that we have introduced in this paper of this idea. So as I said, one could, depending on, in particular, depending on how many new dark fermions you introduce, you can have different realization with different consequences. We have explored a few of them. The one I want to focus is this one, where we have introduced two dark fermions in order to achieve anomaly cancellation. So the theory is anomaly free. And here we have the various terms with the kinetic mixing term here, the scalar mixing term here, and then the mass matrix for the Yukawa couplings for the active, sterile, and dark neutrinos, which will ultimately lead to neutrino masses. Of course, the scale of this new theory is not set and could be very heavy, could be relatively light. In order to look at these anomalies that I'm going to discuss later, I will focus on a GeV scale. So I assume that the wave of the scalar and consequently the mass of the Z prime sit at the GeV. So as I mentioned, this will lead to neutrino masses. The mass matrix here is complex, but it resembles the one that I discussed earlier in case of an inverted or extended seesaw. And depending on the hierarchy that you take among these parameters, these new Dirac masses in the dark sector, mx, these lambdas, and this, which is the Majorana mass term for the for the sterile neutrino, one will achieve different orderings for the masses of the sterile neutrinos and indeed different phenomenology. For the purposes of this talk, I will focus in the case in which the two heaviest neutrinos somewhat decouple, and so I'm left with three intermediate mass heavy neutral leptons. Neutrino masses will arise from this mass matrix with two contributions, one by the diagonalization of this mass matrix. There's also a contribution which comes from loops due to the fact that the Z prime now is not very heavy and so can give a loop contribution to neutrino masses which could be of the same order of the others. because I require to explain the anomalies quite large mixing angles, indeed, we'll use this, the fact that we have multiple contribution to neutrino masses, requiring a little bit of fine-tuning between them in order to explain the neutrino masses in the right mass ranges. This fine-tuning is not particularly strong and is not necessarily present in all the realizations of the model. So let me come to now the phenomenology. And so first of all, to the particle content. So we have a new scalar, which gets a VEV in the GV range. We take its mass naturally to be in the GV scale, but we put it heavier than the other masses, so in some sense it decouples from the theory, at least for the purposes of this talk. In the paper, there's various discussion about its phenomenology as well. We have a Z prime or dark photon with a mass that we fixed to 125 GeV. The reason for this is that we try to explain the angular distribution of the MiniBooNE data. If we don't try to explain MiniBooNE, then this mass could range from the MeV scale to few GeV. There is a key important point from the phenomenological point of view, and that is the Z prime decays predominantly into heavy neutrinos, because these dark fermions are coupled under the new gauge symmetry. So the Z prime into dark fermions and heavy neutral leptons is not suppressed by any parameter, while the decay into the standard model particles is controlled by the kinetic mixing, which is very small. So the branching ratio, the dominant branching ratio for the point in the parameter space that I'm considering for simplicity is into the heavy neutral leptons 5 and 6 with a branching ratio around 86%. The branching ratio into the lightest one, and this is relevant for later, of these heavy neutral leptons and 4 is only 15%. And this is critical because this relates to the invisible branching ratio of the Z prime, because although enforced decay, in most of the searches, they decay to with a decay length which is too long to be seen in the detector. So effectively, they count as invisible particles. And so they contribute to the invisible decay rate of the branching ratio of the Z prime. The branching ratio into electrons, which is also critical for searches of this Z prime, is very, very small, as I said, because it's controlled by the kinetic mixing square. I mean, these values, of course, refer to one specific choice of the parameters for this model, which is the one we presented in the paper. And of course, one can explore different options changing the parameters of the model, but I will focus on this for simplicity. We have 3 heavy neutral leptons, which matter, while the other 2 are very heavy and decoupled. One is around 74 MeV, one around 150 MeV, or 146, and one around 220 MeV. Again, these values could be changed. The reason why we choose these values is because we want N6 to decay extremely fast, within a few millimeters. N5 is also very fast, around 2 centimeters. And if you remember that the Z prime decays mainly in N5 and 6, then this will tell you that the Z prime is mainly visible in this model, as it will decay into essentially 4 leptons and missing energy. N4, although with new interactions, still is relatively long-lived, around 10 to the 7 centimeters. Notice that this is much faster than the standard model, so actually this will lead to significant bounds when we talk about the PS191, for instance. Okay. Okay, so with this picture, what I'm going to do now is try to explain the anomalies that are present. And I mean, here we try to explain a variety of them, remaining in a coherent picture. Of course, depending on the new results we will come out soon, one could try to explain only a subset of these anomalies, depending if there is positive confirmation for them or not. So the first one is the discrepancy between the measured value of G minus 2 for the muon and the theoretical prediction. And as you know, the muon G minus 2 experiment at Fermilab should provide new data in a matter of weeks. Now, this is a significant deviation from the standard model and can be explained by a light dark photon with kinetic mixing. This was proposed over 10 years ago, and here you see the contribution of the dark photon to the process. This is the range identified to explain the G minus 2 of the muon, this gray band here. As you see, but this is essentially kinetic mixing epsilon squared. This is quite large values, especially for heavy masses. In our case, we go to 1.25 GeV. And indeed, in the standard picture, this explanation is excluded by the dark photon Z prime bounds. Here you see a compilation of them from a couple of years ago. The value that we need in our model is here, and this star here, and you see is by several orders of magnitude excluded. But these are searches of the Z prime, which is on shell, so it's a real particle, which decays into E plus, E minus. But in our case, the visible bound needs to be rescaled by the branching ratio into the visible channel. And this is weakened for the parameters that we are considering by a factor of nearly 10 to the minus 3. So this bound becomes much, much weaker, and indeed allows this point to be compatible with the data. There are also invisible bounds coming from Z prime decaying into invisible, and one looks for monophotons with a specific invariant mass. And this is the bound here. You can see. This is the bound. So again, the point we need is this star here. And again, this is excluded by a factor roughly 10. However, in our model, Z prime is not invisible nor visible, is semi-visible. And Molabeng, just over a year ago, pointed out that in case in which the Z prime is semi-visible, then these invisible bounds need to be rescaled. And in his analysis, indeed, he finds that the point that actually we need is allowed by the data. There was a subsequent criticism saying that even a small fraction of events that remain invisible still will lead to a significant bound and could create a problem with this picture. But in our case, differently from Molabeng's paper, in our case, really our dark photons are mostly visible for the largest majority of cases, because as I remind you, the Z prime decays mainly in N6 and N5 with an 86% branching ratio. N6 decays immediately within few millimeters into N5 and E plus, E minus, and then this N5 decays itself. So the probability that the Z prime remains invisible is really very, very small, and is mainly due to when the Z prime decays into new 4s. But as I pointed out earlier, the branching ratio for this is only 1.5 per mil. And when it decays into N5 and 4, and the N5 is invisible because it decays outside the detector, we have estimated that, and we find that this branching ratio is smaller than 2.5 10 to the minus 3, allowing for the value of the kinetic mixing which we require to explain the muon G minus 2. When we were looking at this data and this explanation, however, we thought about the possibility then for these monophotons when the Z prime is off shell, and these can, so the process is E plus, E minus, Z prime off shell. This produces a heavy neutral lepton, which then decays after some distance from the interaction point, in particular in the electromagnetic calorimeter, giving rise to a very collimated pair of E plus, E minus, which can fake a photon, and this can happen relatively easily in the electromagnetic calorimeter. So this would look like a monophoton event, but with a distribution which is relatively flat. And so we looked at Babar data to put a bound from this process. But while we were doing so, we actually noticed that the Babar monophoton events have a slight excess compared to the background. The background, so these are the events as a function of the invariant mass, the missing invariant mass, which is given here. And the red is the background. And you see that the data indeed shows this slight excess, broad, rather broad, which actually drops below 20 GeV squared. And the prediction for our model is this. This is the signal, and you can see it has a nice behavior as it drops below 25 GeV squared and actually flattens at higher energies. And this gives a better fit actually to background only, and it's not very significant, just above 2 sigma, but it's something that, for example, Bell 2 should be able to test in the coming with the coming data. So this concerns Z prime. Now I change completely area, and I go and look at heavy neutral leptons, and in particular at the MiniBooNE low energy excess. This is an excess of electron-like events at low energies, so going below, let's say, 0.5, 0.4 GeV, and this has steadily increased in significance over the years. These are the 2008 data where you see these excess over the background. At the time was 3.6 sigma. And then there was subsequent reanalysis, and the last one, and I'll show you here, is of basically a year and a half ago, in which the significance has increased to 4.8 sigma. So as you see, there is an increase at low energy, and there is as well as a angular distribution which is relatively flat. It's not a very forward signature, as I will show you in a minute. Now, with the release of this new data half a year ago, they increased the number of neutrino data, and then they also performed a more detailed analysis, or refined analysis, if you want, of the backgrounds, trying to exclude any possible source of electron-like events, in particular pi zeros, delta resonance, etc. And the excess remains. Now, as you know, MicroBooNE is currently taking data and analyzing the first set of data. And I mean, anytime soon, it should be a matter of maybe weeks, not maybe months, we should have the first release of MicroBooNE data, which will be able really to look at the fine structure of these events to distinguish them, in particular from pi zeros, looking really at the shower very close to the vertex. As I mentioned, the other information comes from the angular distribution, and as you see, this is relatively flat with a slightly forward enhancement, but events also at angles in the backward direction. Now, the simplest explanation of this excess is with neutrino oscillations, which is compatible with LSND, but there are two reasons why a lot of work has gone into trying to find alternative solutions. One is that the values of the mixing angles required to explain MiniBooNE and LSND are incompatible with the other searches, in particular disappearance searches. There's a strong tension there, and there is a very strong tension with cosmology, as for these mixing angles, the sterile neutrinos should be thermalized in the early universe, and this is not allowed by cosmology. The other reason, which for me is equally important, is that the fit that neutrino oscillations give to the data is not very good. In particular, it is not able to reproduce this enhancement at very low energies. So, building on an initial idea by Nyyenko, which pointed out that indeed MiniBooNE cannot really distinguish electrons from photons, we proposed a different solution in which we have a muon neutrino coming into the MiniBooNE detector, scattering via the Z prime with the protons and neutrons in the detector. Then a fraction of the time, this will produce a heavy neutral lepton, and this heavy neutral lepton, if decays sufficiently fast, will go into E plus E minus. Now, if it is sufficiently boosted, these E plus E minus will be very collimated, so they will look like an electron in MiniBooNE, or a significant fraction of the time, there is a strong asymmetry between them, and there is a threshold for electron detection, and therefore only one electron will be revealed, again mimicking an electron signature. We did a detailed analysis, in particular in the paper that we have recently wrote, we have provided not just a phenomenological model, but a concrete realization in which in the detector, in MiniBooNE detector, one produces new 5s and new 6s, and these then decay, producing the E plus E minus signature that then with a certain efficiency, roughly of 30%, can be misidentified as a single electron and contribute to the MiniBooNE events. And here you see the fit to the energy, which is indeed quite good for these choices of the parameters. So these are the parameters which give us a particularly good fit to energy and somewhat angle. Concerning the angular distribution, our signal, as most of these type of explanations indeed, is relatively forward, but still provides a reasonable fit to the angular data. This is the reason why actually we set the mass of the Z prime to 1.25 GeV, because for smaller Z primes, this distribution becomes extremely forward with essentially no contribution to the other beams here. And in that case, really, there is a significant tension with the data. And in fact, neutrino electron scattering searches, in particular CHARM2 and Minerva, put strong constraints on the light Z prime explanation. And this is, as I said, is the reason for going to heavier Z primes, at least in our realization of the model. So this is the kind of the key part of our analysis. I want to mention in few minutes various anomalies and bounds which were found in the 80s and 90s. These, of course, they can be just experimental anomalies, but if they can be actually explained in the context of our model. And so if you want for, as a for a little bit of fun, I'm going to show you all these anomalies which are buried in these papers of the 80s and 90s. So the key signature of our model is the upscattering of N6 and N5 in the detector with the subsequent decay, as in the exactly as it happens in MiniBooNE, giving rise to electron-like events if, as in MiniBooNE, either one of the electrons is too soft or they are very strongly collimated. I should point out that because N6 and N5 decays very fast, in particular N6, many times these electron-like events will start very, very close to the vertex. And in the searches of the 80s and 90s, the way which was primarily used to distinguish electrons from photons was the distance of the shower from the vertex, with photons starting the shower quite far away from the vertex. In our case, the shower starts right at the vertex in the case of N6. And so these could indeed mimic an electron-like signature in these experiments. I should also point out that there is a very unique signature, which is double vertex events, because there is the upscattering of N6, and then the N6 decays into N5 E plus E minus. The N5 can indeed decay itself, and if it is sufficiently boosted, it will decay tens of centimeters, even meters from the vertex. So we into again E plus E minus. So we will have a vertex with E plus E minus, and then a subsequent event a few meters away. This would be a smoking gun signature of the model. So as I mentioned, 80s and 90s, there were many different types of experiments because they were used to search for neutrino oscillations. But in re-evaluating these bounds, one has to be very careful to take into account the key points as I already mentioned, the cuts to distinguish electrons from pi zeros, in particular photons, the fact that we have magnetization, but in our case, we have both E pluses and E minuses, and the fact that the cross-section in our model, because the Z prime is relatively light, increases very slowly compared to the standard model cross-section, which instead goes quadratically linearly with the energy. And therefore, we expect less events in our model if we go to very high energies compared to the standard model sterile neutrino searches. So I don't have a lot of time, so I'll go relatively quickly. The first anomaly I want to mention is this PS191. And they did find an excess of electron-like events, and they call electron-like events the ones that shower very, very close to the vertex. This is this first chamber here. As I said, this can be explained by N6 into N5 EE events. And this was subsequently tested by 8816 at BNL. They also found an excess of electron-like events. And again, they consider electron-like events the ones which have this distance of disconnection is the distance from the vertex to the start of the shower. Although the significance is lower because they had larger systematic errors. And there is a very kind of interesting anomaly, which is the CCFR double vertex anomaly, in which they looked for double vertices. So a first E plus E minus, or a first shower close to the interaction point at the vertex, and then a subsequent interaction a little bit farther down the detector, a few meters. I should mention that CCFR was at very high energies. They saw this in the neutral current double vertex events, but not in the neutral current charge current double vertex events. This is what you would expect if this was due to heavy neutral leptons in the standard case. Now, again, as I mentioned already, this would be the smoking gun signature for our model, and indeed they have an excess of 9 events over a background of 3. I mean, I don't want to kind of elaborate further, but indeed it would be very interesting to try to look for these type of events in upcoming experiments which can look for double vertices. There are additional anomalies, but I don't want to, which are, if you want, less significant and maybe less important. I just flash them here due to time. Nomad as well, which puts strong bounds, but again, they have an intriguing excess of positrons, and indeed we expect positrons in our model. Let me instead spend a minute on bounds. The bounds come from heavy neutral lepton searches. I already discussed the ones coming from Z primes dark photons, and the most stringent bound is the one coming from PS191. Now, there's no bound for N5 and N6 because these decay very fast, so they would have completely decayed before reaching the detector, so there's no bound. But for N4, this is instead relevant because this is N4 decays faster than in the standard model, so one expects more events in the detector, but nevertheless, the point that we've chosen is compatible just with the bound posed by this experiment. And I just flash here, the, PS191 has actually an event of this kind in which you have 2 tracks, and this should be it's unlikely that this is actually a pi zero because, or a photon, because the photon really cannot convert. This is essentially vacuum here in between. This should be a photon which converts in the flash tube. This can very well be, but this could also be 2 electrons, and then 2 electrons would be exactly the signature that we have in our model. But as I said, this is really not significant at all. It's just a comment in passing. The other relevant bounds are peak searches. But as my student at the time pointed out, peak searches, although they are nearly model independent, nevertheless, they require, for example, the kaon decay, that there is only the muon and missing energy, nothing else. But in our case, the heavy neutral lepton will decay very fast if it is an N6, and therefore will have additional charge particles, in particular additional electrons attached to the kaon decay vertex, and therefore this will be disregarded as additional backgrounds. And so this bound and can be weakened. In the case of E949, we expect at least a factor of 20 or so. And so the point that we require for our analysis is this star here. Now this bound becomes weaker by a factor of 10, is very well compatible. For N5 and N4, the bound applies as is because these decay too slowly, but there is no bound for the parameters we have chosen, for the masses we have chosen. As I said, the smoking gun signature is displayed vertices, so there are experiments, in particular MicroBooNE, which could look for these type of searches, the SBN program at Fermilab, DUNE near detector, NA62, BEL2. And so there is a variety of experiments which are currently running, and it would be important to analyze their data looking for these type of specific signatures, because otherwise they could be missed due to backgrounds. And so let me come to my conclusion. So I argued that a natural extension of the standard model is one in which we have a dark sector or hidden sector, which is complex. I centered around the idea of a gauge symmetry, which then implies the existence of a gauge vector and requires a scalar sector to break the symmetry and dark fermions charged under the new U1. And if we have this kind of three portal picture, I showed you that there are three ways for the standard model to talk to the dark sector via the neutrino portal, the Higgs portal, and the vector portal. And this leads to a phenomenology which can be very different from the one for each individual portal taken individually. And in particular, I've shown you that for a specific choice of the parameter space and a specific realization of this three portal idea, one can explain in a coherent picture the muon G-2, a Babar monophoton excess, which is present in the data, the MiniBooNE low energy excess, and several anomalies in all the accelerator neutrino experiments, which would be indeed very interesting to test in the upcoming experiments which are currently running. Thank you very much.
Thank you very much for the nice talk. So now, any questions from the audience?
Please. Please, Jörn, you go first.
Okay, thanks. Ciao, Silvia.
Hello,
Could you remind me of your N4, 5, 6, which of these neutrinos are mainly your dark neutrinos with a U1 charge, and which is mainly the singlet without charge, or is everything very mixed so that the question doesn't make sense?
No, they are relatively mixed. Well, they are mainly well, I can show you. Maybe I can take the paper and show you, because it depends on the specific realization. We have shown in the paper two benchmark points. We have slightly different realizations for this. So let me see if I find the paper and I can. If you just give me a second here, let me see if I can share again the screen. Share screen, here it is. Google Chrome, let's see if it works. Here, so this is provided by the mixings. Let me see if I have them handy. So there's, well, okay, you can see it here. Well, it's not the best place. Here. So it depends. It depends a little bit. Okay. I want. Oh, it's in the app. Sorry, this is taking a bit of time. So in any case, what you want is for these sterile neutrinos. Here they are. So it depends. For instance, in this case, N5 is not charged under the active neutrinos, so it doesn't couple to them directly. While they are all charged under the new gauge symmetry. In this case, instead, all of them are charged under the new symmetry, under the active, with mixing with the active neutrinos and under the new symmetry. And this is what leads to the bounds, for example, from PS191, from peak searches, etc. While this controls the branching ratio and the decay rates of the heavy neutral leptons, as this is mainly due to the Z prime.
But didn't you say you have only two neutrinos charged into the new U1 because of anomaly cancellation?
Yeah, but they mix all together. These are the flavor states.
Oh,
right?
okay. Yeah, fair enough. But thanks.
Yeah, so this is DL, if you want, is one of the two sterile dark fermions, and D right is the other one. But then they all mix together. Does this answer your question?
Yes, thanks.
Hi, Professor. Your recent work has been in the center of our attention recently. So thank you for the opportunity of making questions directly to you and for your talk, of course. My questions are just too elementary, but in page 31 of your talk, you just mentioned that you introduced the 3 new sterile neutrinos. And my question is there a particular reason for this choice of 3? Because I know that one, of course, wouldn't provide the correct 2 eigenvalues would be 0 for the active neutrinos, while 1 eigenvalue would be 0, which is in principle okay. So would it be possible having, instead of 3, having a different or having 2 new sterile neutrinos to fit with your purpose in the work?
Yes, you can surely do that. Of course, I mean, the idea behind having 3 is that somehow we think of these sterile neutrinos as belonging to somehow an extended standard model.
Sure.
And in that way, for me, it's relatively natural to have it filling the same kind of generation structure as the standard model, so 3 of them. And these would allow also, for example, to gauge B minus L if one so wanted.
Yeah.
Concerning neutrino masses, for example, in this specific case, we were more focused on the phenomenology. So we didn't really study in detail how to explain all neutrino mixing parameters, which we're planning actually, what we're currently doing in a different study. So maybe it's possible to do it only with 2 sterile neutrinos. But then what I want is really to have these 3 intermediate states all together around the sub-GeV scale, because that allows for this rich phenomenology. So, I could lower one of the heavy neutrinos, but the 2 ones which are decoupled, but then what I would need to do is kind of change significantly the hierarchy of masses, etc. So maybe in principle it's possible. It should be looked at in detail.
Thank you. So you use the concept of a dark photon and of a Z prime interchangeably, as you mentioned. However, if I am correct, but I noticed that maybe in the literature and the community is trying to discuss about concept of dark photon and Z prime by distinguish them according to how they couple with either a vector current in the case of dark photon, so they couple as the photon, or they couple as a Z, so in the case of the Z prime, which means that they basically differ by the presence of a vector, axial vector component. So, but if this is the case, there's the bounds that you use directly apply to the Z prime case, like when you use dark photons bounds to your U1 theory.
Okay, so I mean, we call it a Z prime. I mean, you are right that we should have used just dark photon. Ours is a dark photon. It's only a vector coupling to the electromagnetic current. So we don't introduce mass mixing with the Z. In any case, that would be completely subdominant because our Z prime is quite light. So I like to call it Z prime because there is this kinetic mixing with the B, but it is true. I mean, technically speaking, it's a dark photon. Maybe we should actually align with the common literature and call it throughout a dark photon. And because it is a dark photon, the bounds that I discussed are the dark photon ones. So in particular, for example, this doesn't couple to the neutrinos, which is quite relevant if we're looking, for example, at neutrino scattering, etc.
Yeah, if they don't couple with neutrinos because you have this phi, which is supposed to be light, and hence it's VEV as well, and the mass mixing goes with the mass of the Z prime. Okay.
Yeah. Oh. So it's very suppressed. It couples only to the electromagnetic current significantly. But I should say it couples to the neutrinos via a neutrino mixing, but that is very small.
Yeah, as you said, true. Okay, so just the last question about the MiniBooNE. In page 42, you just have the Feynman diagram representing how to explain the MiniBooNE excess in the framework of your model, which is through the production of the heavy neutrinos by the exchange of a Z prime. And
here it is.
Yeah, and my question is, how would be the process, like the diagram itself, in the standard case, like in the general case, which means mediated by in the framework of standard model plus right-handed neutrinos? How would it be?
Yeah, so you just exchange a Z rather than a Z prime. The problem with that is that the decay of the N is too slow.
But if you just change a Z instead of a Z prime, from where comes the charge field, like the electron? Because the MiniBooNE
from the Z, the E plus E minus from the Z.
Okay.
So here I can have just a Z instead of a Z prime.
In your case, in your case, it's a neutrino and the target exchanging a Z prime, producing a heavy neutrino, which then decays into electron-positron pair, which cannot be distinguished with just an electron.
Yes, in MiniBooNE, yes, with a certain efficiency, which you can estimate 20–30% depending on the model.
Okay, because what I was thinking is that we discussed this, which would be a neutrino and the target, and then a charged current producing an actual electron, just one electron instead of electron pair, by the exchange of in a charged current process, but this would change the atomic number of the target. And my question is, if this is distinguished, if you can just distinguish that in both cases, like in a case where,
So not in MiniBooNE, because MiniBooNE doesn't see the hadronic part. It is a scintillator detector. So you see only particles which are sufficiently fast to give you scintillation light. Okay. While in microBooNE, in principle, yes, because you should be able to see also the hadronic component. So the standard explanation of the electron-like events in MiniBooNE is you have new E coming in, exchanges, well, it could be a neutral current, it could be a charge current, and it gives you an electron. You don't see the hadronic part, so you just look at the electron in the process, and that is just nu E scattering in the detector. And then you have to explain where the nu E comes from. And so the nu E comes from neutrino oscillations.
Perfect. So then you don't see the hadronic part at all. So you don't pay attention.
Yes.
You cannot distinguish between that. Perfect.
Yeah.
Okay. Just that. Thank you very much. Thank you.
Hello. Thank you very much for a nice talk. And I have a question about your explanation for the MiniBooNE. So
Sure.
in your case, you will have a electron-positron pair in the final state, right?
Yes.
And in certain cases, both of them can be can leave some traces in the detector, right?
Yes.
So when you fit your when you explain this MiniBooNE access by your model, how many events do you expect that the if both electron and the positrons are leaving their traces in the detector, and is that does it? I mean, does the experiment actually record that kind of event or not?
Well, in principle, yes. So we have an efficiency of roughly 10%. So we assume that roughly 10% of these E plus E minus events are misreconstructed as a single electron. Either because they're very collimated, but most of the time because one of them is too soft. This was a consideration actually that my former student at the time, Ross Lonergan, found. Now, what happens to the remaining 90%? Well, they look like E plus E minuses. In particular, they look like photons, two photons. So they will, part of them at least, will contribute to the pi0 sample. But because the neutral current rate is much higher, and these will be relatively flat in energy, they are still below, I mean, they are within the errors of the pi0 reconstructed events.
Oh, I see. Okay. And in your model, do you have any other testable signatures in, for example, kaon physics or other meson physics?
Yes, yes. So, well, I mentioned it very, very briefly. But so the key signature would be, but first of all, these E plus E minuses with the vertex in MicroBooNE, SBND, DuneND, T2K near detector, etc. They will come up in kaon decays, but so one should look not at the kaon peak search type of bounds, but at kaons in which at the vertex there are additional electrons. So, and one should kind of be careful and distinguish that from, for example, muon, neutrino, photon background. But here you have any plus E minus which showers, I mean, which is really attached to the vertex. So if you have enough resolution, you should be able to distinguish from, I mean, this E plus E minus pair coming from N6 decay from a photon which showers farther from the vertex. And then really a key signature is a displaced vertex. So if you have a sufficiently large detector, for instance, an A62 or SHIP, then you could see the two vertices. The first vertex coming from when the N6 decays and the subsequent decay of N5 few meters down the line.
I see.
Like they've seen, for example, in CCFR. So that would be kind of really a smoking gun signature because it would be related to the presence of both N5 and N6. So two heavy neutral leptons with light, with very fast decays.
Okay, thank you.
Ciao, Silvia. May I?
Oh, hello, Francisca.
How are you? I have a very silly question, actually, the question of a person, an ignorant person. I had no idea of the existence of MicroBooNE. What type of experiment? Is just like MiniBooNE upgraded somehow? What is it?
Okay, so
if you can say a few words without wasting too much time because it's late for you.
So MicroBooNE is essentially it's been built to test MiniBooNE. It uses the same accelerator complex. So it's at Fermilam, we use the booster beam, so same energies, the same type of flux, etc. But the key difference is that MicroBooNE uses liquid argon, while MiniBooNE was a scintillator detector. And because MicroBooNE is a liquid argon detector, it has extremely fine abilities in reconstructing the structure of the events at very, very, very small distances. So it can reconstruct the vertex, the shower, the hadronic shower, and then the electromagnetic particles, distinguishing very well pi zeros, so photons from electrons.
Okay.
And so this is is an ideal configuration for these type of searches, because you really want to look at the fine structure of the event, the topology of the event, to distinguish it from standard model processes. Indeed, we are working with MicroBooNE to look at these type of models we're still at the level of simulations, but I'm working with Asli, my student, and Matteus, who was a former student of mine, with the MicroBooNE collaboration, exactly to look at this. And importantly, there's not just MicroBooNE, but there's also SBND and Icarus at SBN at Fermilab. So there are 3 detectors which will use the same beam, and which are all liquid argon detectors. And so one could do comparisons between the 3 detectors and will have much better sensitivity than MicroBooNE alone. And then DUNE-ND, for example, also will have a liquid argon component with magnetization. So again, could have excellent capability to test this type of models.
Oh, very good.
I don't know if this is enough detail. I mean, I can go into more detail
No,
if you
no,
want.
no,
This
very
is the
good.
basic of
I had no
MicroBooNE.
idea of what it was. So no, that's very good. Thank you so much.
So maybe just to add that MicroBooNE has been running now for many, many years.
Oh, I had no idea. I didn't know.
It's a Fermilab. Somehow they encountered significant delays because apart from Icarus, this is the first time that one tries to do automated event reconstruction in a liquid argon detector. And because the topology of the events is very complex, especially at higher energies, this turned out to be a very significant experimental issue, which, however, needs to be resolved because DUNE is using liquid argon. So event reconstruction in liquid argon has been now a key topic for several years. So now they are at the stage in which, to my knowledge, they're analyzing the data, and I expect some results maybe in the summer.
Oh, wow, good. Very good. Thank you so much. Thank you.
I have a question about your comments on the Babar result in slide page 37. So in that page, you show the Babar data overlaid with the background fit and some signal portion. So how confident are you about this background function? I mean, what is the uncertainty about the background shape and the background amount?
Okay. I'm as confident as the collaboration, in the sense that we didn't try to model the background ourselves. So we have taken that at face value from the collaboration. So of course, this will have significant error associated to it, and indeed one should. But the best, rather than trying to second guess the data from the collaboration, I think the best is to look at what Bell2 can do to test this, because they will have a very similar signature.
Thank you.
So we also didn't want to put too much emphasis on this, because somehow nobody really pointed out this excess, which in my opinion is there. I mean, you see there's also two possible peaks here, but these were discarded by the collaboration as any significant hint of dark photons. So we just wanted to point this out as actually a prediction of our model, if you want.
Yeah, so it will come down to how confident we understand the background. Yeah.
Well, yes. I would say so. Okay, there are two aspects. One is that, and the other one is not really possible to make a detailed prediction of the number of events of the signal without doing a full analysis, a full Babar analysis. And they use some machine learning techniques to distinguish background from signal that are not available to us. And so we made essentially a guess on the mis-ID'd. This all relies on the fact that you have to mis-ID any plus C minus pair in the electromagnetic calorimeter. And so what we pointed out in the paper is that, we need a mis-ID rate, a probability of mis-ID of around few percent. And this appears very kind of reasonable given the experimental configuration and the tools they use for this reconstruction. But if you want really to know, if it is 2% or 3%, which then enters in the number of events that we predict, that you need to do the full Babar analysis, and that is not possible for us.
Yes, I agree. Thank you.
Okay, any other more questions? Yeah, if not, let's end today's seminar. Thank you very much, Silvia.
Thank you very much.
Thank you.
Thank you. It was a pleasure. It was a pleasure really to discuss physics. Bye-bye. Django, could I ask you a question?
Yeah, sure.
Because I've seen that you have done a Bell analysis, right? For Mola-Banks type of model.
Yeah.
So I wanted to know if you had an opinion on how this model would look like in Bell.
What do you mean?
So our model, I mean, if there would be a difference compared to Mola-Banks model, or it would look similar.
So your model, you mean?
Yes, yeah. Because we're thinking about that, of course, no? Because Bell would be, the way to that could see the signatures and have a way. So I wanted to, to have if you had a feeling on that.
So event-wise, it looks very similar, I think.
Yeah.
Could they have at all any sensitivity to double vertices? So one at the interaction point and one farther out?
So if if the decay, I think it's depend on the decay length of the N6 and N5. So if both of them can decay inside the detector, maybe Bell also can find both vertices, but
and so what is the improvement of Bell compared to Babar?
Actually, Youngjun was the experimentalist, but he left now. So,
Okay. In any case, I'm reading your paper with interest, and I think
Yes. I think that in our case, we studied the search for excited dark matter at Bell 2. And I think the signature is very similar to your model. So I guess your model also can have can be searched for at the Bell 2. Yeah, that's my guess. But we can also talk with Youngjun, the Bell experimentalist, and also communicated with you too after we
that would be
talked.
very interesting for
Yeah.
us.
Yes, yes.
Because I think the main difference with Molenbeek's dark matter model is that in our case, there's less invisible events.
Right, right.
It's
That's right.
mostly visible.
Yes.
And as I said, in some cases, you have these additional vertex. Although, okay, well, you have the interaction point, so it doesn't matter too much that it doesn't point back to the direction. But actually, that could be an advantage because you would have an additional vertex where the charged particles don't point back to the interaction point. Because you have missing.
Yeah, right. Yeah, in your case, yes.
Yeah, so that could be somewhat useful to distinguish from background. But it was thank you very much. I mean, for inviting me to give the talk. It was really nice to chat about the physics.
Yes, thank you very much for accepting. I mean, giving a very nice talk and discussions. Yeah. So bye bye.
Bye bye. Bye.
Silvia. Oh, yeah, she left.
Well, anything missing?
I want to ask us to send the talk file.
Oh yeah, you
The
can
other
send an
email.
email. Yes.
Yeah.
Yeah. Thank you. Bye bye.
Bye bye.